All right, picking up where we left off last time. Last class, we talked about bonding. We very briefly looked at Lewis structures, Lewis models, Lewis dot structures, where we have the symbol for our chemical, for our atom, and then we surround it with dots equal to the number of valence electrons that it has, which is based on the column or the group that it's in on the periodic table. And we are going to get to the actual rules of how to put together Lewis structures and some extra stuff that we can do in Chem 1 that we weren't able to do in Chem 10 or Chem 20. So just as a reminder, we've got several types of bonds. One of them is covalent bonds. Covalent bonds are between two things, the co, like in cooperative. They're sharing their valence electrons. So covalent bonding is occurring only between two atoms. They're really strong, but they're super directional. They're just between two things. Unlike ionic bonds, where you've got alternating positive and negatively charged ions. And then the weak forces between the molecules means that we tend to have lower melting points for these. So a lot of things that have covalent bonds, especially if they're smaller, have relatively low melting points and are often liquids at room temperature, if not gases. We also have electronegativity. So electrons as dots is a very big oversimplification of what's actually going on. We've done some of the quantum mechanics stuff. We know that they're not actually just dots. We know they're not actually just sitting in one spot the whole time. They're not even just flying around in orbits. It's more complicated than that. As it turns out, sharing electrons equally is also not accurate. That's also an oversimplification. So we can ramp up our complexity very slightly. So in polar covalent bonds, we have unequal sharing of the electrons. The polar, like having poles, this is poles like the North Pole, South Pole, positive, negative pole, like for magnets. Having ends that are opposites. So polar covalent bonds, so they're still covalent bonds, we're still sharing the electrons, but we've got positive and negative parts. We've got north and south parts. And so there's unequal sharing of the electron across the bond. And this is an intermediate. It's between ionic bonds and pure covalent bonds. This is our like middle ground. I'm going to write middle option. So they're not a full transfer of electrons like in ionic bonds, and we're not sharing them completely like in pure covalent bonds. So things like hydrofluoric acid, or HF, fluorine, really, really likes electrons. And so it's pulling the electrons towards itself. The electrons are more often found near fluorine. It's got a stronger electron pulling force, and so hydrogen is sort of getting robbed. It doesn't get as much time with the electrons as it would like. Fluorine's sort of the big sibling in this situation. Hydrogen's the younger sibling in this situation, and fluorine is hogging all the toys, to give us an analogy. We've got a scale that measures the ability of an atom to attract those electrons to itself in a chemical bond, and that's electronegativity. So electronegativity is how strongly an atom pulls electrons in a bond. Would be another way to put it. So in my mind, I usually think of this as a tug of war. You've got two atoms, those represent two people. The electrons in between, they're both pulling on them. And electronegativity is their stat that determines how strongly they pull on the electrons. If you've got a higher electronegativity value, you're pulling stronger on those electrons. The electrons are closer to that thing. And here's our periodic table with a scale. Over here in the bottom left corner, we've got the very lowest values in the top right corner with fluorine at 4. Those are the highest values. Noble gases are unreactive, and so we don't include them. The one that you should know for sure is fluorine. Fluorine is a 4. A 4.0 on the scale. That's the highest value on the scale. There's no AP classes for electronegativity. You can't get up to a 5.0. So fluorine maxes out the scale at 4. If fluorine gets in a fight for electrons with anything else, fluorine wins, unless it's also fluorine, and then they share equally. Fluorine's the big bully of electronegativity. And then things that are close to it also have high values, and it decreases as you move down and to the left. Okay, let's arrange these elements in order of decreasing electronegativity, remembering that fluorine is the ruler, the strongest, the champion of electronegativity, and then the opposite corner is where the lower values are. So we've got nitrogen, phosphorus, aluminum, sodium. Let's see where we find all of these things. We'll get them here in green. Actually, red will show up better. N, P, Al, Na. We want to go in order of decreasing electronegativity. So starting with our highest electronegativity value. Which of these 4 is going to have the highest electronegativity value? Nitrogen, because it's closest to fluorine. It's furthest up and to the right. What'll be next up? What's next closest to fluorine? Phosphorus. So phosphorus is number 2. Then up next, aluminum, and then last but not least, sodium. So incidentally, it's A, the one that I read off. That's going to be our order from highest to lowest. You should generally be able to solve something like this where you arrange them from highest to lowest. You wouldn't necessarily know the numbers that are associated with them. If you need the numbers, I'll give you the numbers. If you have the yellow sheet handout, it has the electronegativity values in it. If you look at the fluorine box, I think it's down and to the right, or maybe it's down to the left. There's a 4.0 in the fluorine box. That's the electronegativity value on that yellow sheet handout that I've given out before. If you need another one of those, I still have some extras. And then this will probably never come in handy, but I think it's the first 10 most electronegative elements. There's a mnemonic device that I learned when I was in undergrad, and for some reason it's still stuck in my mind. And it's this, it's Fonkel brick ship. Because my brain decided that this was important to hold on to. Fonkel brick ship. That's the order of the most electronegative elements. Some of these are like tied. Like I think nitrogen and chlorine might be tied, or maybe it's bromine and iodine. Some of these are really similar values, but roughly speaking, this is from highest to lowest. So fluorine's a 4, and then hydrogen is like a 2.1 on the scale. So it's a pretty rapid decline in electronegativity, just for those first 10 elements, or however many it is. Okay, so we've learned about electronegativity. Higher electronegativity, stronger ability to pull on the electrons. We're winning the tug-of-war battle. And this affects bond polarity. So we talked very briefly about polar covalent bonds. We've talked a bit about ionic bonds, and pure covalent bonds have also been mentioned. The degree of bond polarity depends in part on the difference in electronegativity. Electronegativity we can abbreviate as En, and then difference gets the delta symbol. So our change or our difference in electronegativity between our two bonding atoms. And these are sort of just loose guidelines. In reality, there's a whole continuum of bond strength. So from 0.0 all the way up to 3.3. It's a continuum. At 0.0, they're purely shared. At 3.3, that's the most electron transfer that we can get. And it's just kind of a sliding scale in between. So these are sort of arbitrary cutoffs. But our cutoff values are 0.4 and 2.0. If it's below 0.4, we would call it a nonpolar bond. If it's between 0.4 and 2.0, the electrons are shared unequally. So that's going to be our polar region. We get a partial negative charge on the thing that's more electronegative. We get a partial positive on the thing that's less electronegative. And then once we get above 2, that's when we call it an ionic bond, and we've got full electron transfer, negative, positive. The one with the higher value is the one that steals the electrons. Any questions so far? All right, we'll see some of the same information, but in a table on this next slide. So the dipole moment is another way that we can measure bond polarity. Dipole moment, which has the Greek letter mu, like the sound a cat makes, a kitten makes, occurs whenever there's a separation of positive and negative charge. Dipole moment is measured as the charge times the distance, and a common unit for that is the debye, which gets the symbol d. And this c here is our charge. That's the coulomb. M here is the radius, the distance. That's where those units come from. Don't expect that we'll be doing much with calculating dipole moment. Maybe a little bit, but probably not much. More important would be learning the electronegativity difference values. So 0.4 is our cutoff for pure covalent or nonpolar. Like in Cl2 or anything where it's the same atom bonded to itself. Atom is bonded to another of the same atom. There's probably a shorter way to write that. So Cl2, N2, O2, H2, F2, I2, Br2, any of those 2s, you're going to get a pure covalent bond, a nonpolar bond, because they have the same electronegativity value. They have to be sharing those electrons equally. If we ramp up to the 0.4 to 2.0, that's where we get polar covalent bonds, something like HCl. Hydrogen's a 2.1. I think chlorine is a 3.5 or a 3. I don't remember exactly. And then for things with large electronegativity differences, anything above 2, we would classify that as ionic, things like sodium chloride. There's another way that we can classify stuff as having ionic bonds. Any guesses on what kind of compound has ionic bonds? Thinking of nomenclature categories, naming categories. What kind of compounds might have ionic bonds? Ionic compounds have ionic bonds. That's exactly right. Ionic compounds have ionic bonds. This is generally true. There might be some exceptions where we're actually below this difference in electronegativity of 2, but usually that's a good way to tell without looking at any electronegativity values. If you have an ionic compound, a metal and a nonmetal, then it's probably going to also have ionic bonds, because our metals live over on the left side of the periodic table, nonmetals live over on the right side of the periodic table. So we're getting something with a high electronegativity value in the top right, low electronegativity over on the left or on the bottom left. Okay, and we have said before that anionic compounds were transferring electrons, which is not true entirely. We are transferring electrons, but not 100%. So it's not actually yoinking, our nonmetal is not yoinking the electron away from our metal. It's definitely bullying our metal, and it's stealing it most of the time, but it's not 100% of the time. So a way that we can calculate, or a way that we can talk about how ionic something is with percent ionic character. So we've got a graph. We've got electronegativity difference on the x-axis. We've got percent ionic character on the y-axis. As we're going left to right, we're looking at things that are further apart in the periodic table, bigger electronegativity difference. On the y-axis, percent ionic character, if we're at 100, that means the electron is completely taken. It's actually transferred, formally transferred. At 0, they're evenly sharing. It's not transferred at all. So if we look at the trend, as we go to a higher electronegativity difference, our percent ionic character also tends to creep up. It's not exactly a one-to-one relationship, but the bigger our electronegativity difference is, the higher our percent ionic character. Notice that none of these are at 100%. Some of them are pretty close, at like 90% maybe for lithium fluoride. So when we're talking about it being ionic, the electron being transferred, it's not actually completely 100% transferred. It's like 50% transferred, whatever that would look like. And this is at a 1.9 electronegativity difference, our HF here. Notice that everything up above this 50% ionic character, which we consider ionic, notice that these are all ionic compounds. So that's really convenient. Further evidence that if we have an ionic compound, a metal and a nonmetal, we can just go ahead and say, yeah, it's got ionic bonds, even if the electronegativity difference is not over 2. Question?
On the second to last slide, what does it mean by saying the divisions are arbitrary?
On this slide?
Last.
This one. It's just kind of like rough cutoffs. It's sort of like if I asked you what's the difference between, like, money-wise, how much money does somebody who's poor have, how much money does somebody who's like middle class and then rich? There's not like really a cutoff where it's like if you're above this amount, suddenly you're middle class. If you're above this amount, suddenly you're rich. We kind of just made it up. So these are just kind of rough guidelines. If you're below 0.4 electronegativity difference, then they're basically sharing completely equally. If you're above 2, they're basically generally going to be ionic. Other question?
If we get a difference of like 0.4, which is like on the border between covalent and polar covalent, what would it be considered as?
Yeah, if it's at 0.4, then I would say it depends on what we're trying to do with it. If we're trying to say, is it an ionic, or is it a polar bond or a non-polar bond, I would probably lean towards it being non-polar. If we're just talking about the bond, if we're trying to assess, is, as part of like a bigger molecule, like the shape of the molecule, is it contributing, is it a polar compound, which we haven't gotten to yet, then I would say, let's go ahead and assume that it's polar and see if the molecule's shape actually helps with that, or if it cancels it out and it's not polar. So a big shrugging emoji, essentially. Depends. Did I answer your question about the arbitrary?
Yeah.
Cool. Yeah, so rough guidelines, it's not always going to be, they're not perfect. Okay, knowing what we know, let's determine whether the bond formed between each of these pairs of atoms is nonpolar covalent. They're sharing perfectly like our kindergarten teacher would want. Is it polar covalent? They're not sharing, but they're also not stealing. Or is it ionic, where they've basically stolen the electron? So I'll give you some time to think about it, discuss with your neighbor, and then we'll come back. All right, I added the electronegativity values in there as well, in case you needed those. Let's figure out what sort of bonds we have. So first up, we've got I and I, together that'd be II. Yes, Captain? Iodine is the same or something different than iodine? If we've got these two things bonded together, are these the same or are they different? They're the same. They're the same element. So even without the electronegativity values, we should know they're going to have the same electronegativity value. So it has to be perfectly equal sharing. The sharing is equal, and that means that it is nonpolar or pure covalent. Every time that it's a thing bonded to the same thing, it's always going to be nonpolar because they're going to have the same electronegativity value. Second up, we've got cesium and bromine. If cesium and bromine form a bond, how would we characterize that bond? What would we call it? Nonpolar, polar, or ionic? It would be ionic, and there's two ways that we can come up with that. So the first way, and I think this is arguably the easier way, is it's an ionic compound. Cesium is a metal, bromine is a nonmetal. It's an ionic compound. Ionic compounds have ionic bonds. That's the first way. The second way is the difference in electronegativity. So we would have to be given, look up, or have memorized. Probably don't memorize them. We would look them up or be given the electronegativity values. We'd find that they are 2.8 and 0.7. We take the bigger number and subtract from it the smaller number. So 2.8 minus 0.7. That's a difference of 2.1, which is ionic. It's above that 2.0 threshold. So that would be the other way that we could come up with it being ionic. And then last but not least, we've got phosphorus and oxygen. What kind of bond do we have here? Yeah, we have a polar covalent bond. We know that it's polar covalent because covalent bonds form between nonmetals. Molecular compounds have these. Molecular compounds being made up of nonmetals only, but we also know because of the difference in electronegativity. We take the larger number, 3.5, subtract from it the smaller number, and we get a value of 1.4. And that 1.4 is between 0.4, that's our lower cutoff, and 2.0, our upper end cutoff. If it's below 0.4, it's nonpolar. If it's above 2, it's ionic. If it's in between, it's polar. So they're sharing the electrons, just not quite equally. Questions about any of those three? Great. Here are the steps for making a Lewis structure for a molecular compound. We did Lewis structures for ionic compounds. Molecular compounds is what we're more concerned with, and so here's our 4 steps. Step 1, you need to write the correct skeletal structure of the molecules. What is a skeleton? Does a skeleton have flesh on it? Like if you look at like the classroom one that they roll in, like the spooky, scary skeletons dance. Doesn't have flesh on it, right? It's just what? The bare bones. So for our skeleton structure, our skeletal structure, just the atoms. We're just figuring out where do all the atoms go if we can tell. Sometimes we won't be able to tell. We'll learn some tools for being able to figure out the correct orientation. But we've got some general rules. So hydrogen atoms are always going to be terminal. Terminal means that they are at the end. The reason that hydrogen atoms are always at the end is that hydrogen only forms one bond. Hydrogen, being in our row 1, n equals 1, only has access to the 1s orbital. 1s can only have 2 electrons in it. One bond is 2 electrons, so hydrogen can only have 1 bond. So hydrogen's always going to be on the outside. We will also generally put the more electronegative atoms in terminal positions, the outside positions. It's a good general rule of thumb. So we'll also have electronegative atoms on the outside. Just as a general rule, that's our first step, just figuring out where do all the parts go. The second step, we want to calculate total number of electrons, total number of valence electrons. So we're going to add up all the valence electrons. And if we have ions, then we also need to consider charge. So we're going to add 1 for each negative charge, subtract 1 for each positive charge. And what we get when we add up all the valence electrons, I will abbreviate valence electrons as VE. There's sort of a step 2.5 here that I would add in here that I give my Chem 20 students. 2.5, put in bonds. In order for it to be a molecule, everything has to be connected. And so we would put in the minimum number of bonds just to get everything connected. And those I abbreviate as BEs, bonding electrons. Once we're done with that, we distribute the electrons among the atoms, giving octets to as many atoms as possible. Oftentimes we'll start, the way that I typically do it is starting from the outside. Add from the outside or the terminal atoms and work towards the center. Sometimes we'll run out before we get to our central atoms. We won't be able to give everything full octets. Who remembers what an octet is? What's an octet mean? What are we talking about? A full valence shell, full 8 electrons. So we want everything to have 8 electrons that count towards it, that it's sharing. So anything that's in bonds plus lone pairs. If any of our atoms still lacks an octet, then we can form double or triple bonds as needed to give them octets. Do we have questions so far about these rules? Okay, then let's do some practical examples, because Lewis structures, putting together Lewis structures it's kind of like a little board game, and just like board games, it's often helpful to be told the rules and then learn them as you use them. And so let's get on with just using them. So we'll start off with some more simple things. So we've got CO, carbon monoxide. We want to start off with the skeletal structure. When you've just got two things, it's hard to be wrong. The only way that I would say don't do it is don't put them right on top of each other and work front to back, because that's just crazy. And so as long as they're next to each other in any orientation, it's fine with me. So we'll write it in CO, and then we need to figure out how many valence electrons do we have. We've got carbon, we've got one of them, we've got oxygen, we've also got one of those. How many valence electrons does carbon have? It's in, table moves. It's in group 4A, or 14, so it's got 4 valence electrons. Oxygen is in group 16, or 6A, and so it has 6 valence electrons. So from our carbons, we've got 4 electrons. From our oxygen, we've got 6, so we've got a total of 10 valence electrons. We get to put 10 dots on the board, 10 electrons down to make our correct Lewis structure. In order for this to be a molecule, they have to be connected. So let's add in that step 2.5. We have to put in one bond. How many electrons are in one bond? 2 electrons. So minus 2 bonding electrons, that means that we've got 8 remaining electrons. So now we have to distribute our 8 remaining electrons among our 2 atoms to try to get octets. So the way that I would do it is I would distribute them evenly. So we can get 8 divided by 2. We've got 4 each. I'm going to put them on as pairs, even though that's maybe not technically correct. So minus 4 electrons to carbon, minus 4 electrons to oxygen. So all of our electrons are on the board, and now we have to figure out, do we have octets? So let's look at carbon. Carbon's got 2 from this lone pair, it's got 2 from this lone pair, it's got 2 from the bond. Carbon has 6 electrons. Oxygen has the same situation, 2, 4, and then the 6. So we've got 6 for our oxygen as well. So neither of them has a full octet. Which is a problem. How can we get them to have more electrons? We've already placed all our electrons. Carbon needs more electrons, oxygen needs more electrons. What could we possibly do? Step 4. Form double or triple bonds as needed to give them octets. So we can take these lone pair electrons. Carbon is currently hoarding these 2 electrons, Oxygen's hoarding 4 electrons as well. We can move some of those electrons in to form bonds. So through the power of friendship, let's move in that lone pair. And we'll draw what that looks like. Okay, so we add in another bond. Carbon has donated electrons to make this bond. How many electrons does carbon have access to? Has it changed? It's still 6. We've got 2 from the lone pair. and then 4 from the double bond. So it's still got 6. How about oxygen? How many electrons does oxygen have access to? It's got 2 from this lone pair, 2 from this lone pair, 4 from the bond. 2 plus 2 plus 4 gives us 8. So oxygen has 8. It's happy. It's got its octet. But we still need to rectify the fact that carbon does not have enough electrons. How can we get carbon access to electrons? We add another bond. So we'll steal some or borrow some electrons from oxygen. To make it a triple bond. Now if we check oxygen, it's got a triple bond. That's 6 electrons plus 2 in the lone pair. It's still good. It's still got its octet. It hasn't lost access to any electrons. Carbon has the same situation. It's got 6 from the triple bond, another 2 from the lone pair, and so carbon also has its full octet. So carbon triple bonded to oxygen, carbon monoxide. Questions about putting together that Lewis structure? Yeah.
So basically, just to simplify, as long as some might be sharing more than other atoms, as long as they both have the octet, it should be fine. It doesn't matter if one shares more than the other atom.
I'm not 100% sure what you mean by sharing different amounts, but yes, the goal is octets. When we've got more parts involved, maybe we'll.
I worded that super weird.
Let's look at our next example and see if it comes up again. Okay, so our Lewis structure for H2CO. We need to get a skeletal structure down. We need. Where are we going to put everything? Generally, molecules are going to be symmetrical if they can be. So they'll have left-right symmetry, up-down symmetry. And we know that these hydrogens have to be terminal. So let's start by putting those on the outside. Then we've got carbon and oxygen. We could potentially write it in HCOH. That is a way that they could be arranged, but we get symmetry if we get left-right symmetry if it's like this, or the other option would be this one on the right. One of them is correct. So this is where that second little dot under 1, put more electronegative atoms in terminal positions. This is where this comes in. So if we compare carbon and oxygen, carbon's got an electronegativity value of 2.5, oxygen's got a value of 3.5. Oxygen's closer to fluorine versus carbon. So oxygen, being more electronegative, is going to go in the terminal or outside position. So we can throw out this one on the right, and this HCH, and then the oxygen up above. This is going to be how we start our skeletal structure. Okay, and then we need to figure out how many valence electrons do we have. We've got, we'll do it all the way over here on the right. We've got carbon, which gives us 4 electrons. We've got oxygen, which gives us 6 electrons. We've got hydrogen, we've got 2 of them with 1 electron each. This gives us a total of 12 valence electrons. In order for this to be a molecule, everything has to be connected, so we'll add in some bonds. It might be tempting to do something like this, where we've got these weird triangles popping up. Triangles are bad. Avoid triangles, avoid squares. Triangles tend to explode. Squares are more stable, but they also tend to explode. So avoid squares and triangles, please. So this is the minimum that we need to just to get everything connected. How many bonds did we add in? 3 bonds. How many electrons are in a bond? 2. 2 times 3, we've used 6 electrons. So minus 6 bonding electrons, that means that we've got 6 remaining electrons. And I like to start by adding them from the outside and working our way in. Oxygen currently has 2 electrons. It wants to get to 8. That means that we've got 6 left until it gets to its octet, right? So we can give all 6 of our remaining electrons to oxygen. When we do that, let's go through and check octets, because we've placed all of our electrons. Let's see if everything's happy. Does hydrogen have all the electrons that it wants? Yes, it has 1 bond. 1 bond is 2 electrons. 2 electrons is a duet. Hydrogen likes to have a duet. So our hydrogens are happy as long as they're connected. They just want to be included. Let's look at our oxygen. Oxygen has 2, 4, 6, 8 electrons. Our oxygen has an octet. Our oxygen is all good. How about carbon here in the middle? Carbon's got 2, 4, 6 electrons. Which is not an octet. Where can we get some more electrons to share with our carbon? From oxygen. So we're going to move in one of these lone pairs. And when we do that, we've got a double bond now, which is 4 electrons. Carbon has 1, 2, 3, 4 bonds. It's got 8 electrons, full octet. Oxygen, because it moved them into a bond, still has access to them, so it still has 4, 6, 8 electrons. Oxygen is still happy, it's got its octet, so we are done. Questions about this Lewis structure? As we're initially starting to learn how to do Lewis structures, they will be slow. The more practice that you do, the faster you will be at putting together Lewis structures. There's almost definitely going to be at least one Lewis structure short answer question on the exam that covers this material. Okay. We can also have Lewis structures for polyatomic ions. We're going to add 1 electron for each negative charge. We're going to subtract 1 electron for each positive charge. And just like with our ionic compounds, we get brackets with the charge in the upper right-hand corner, but around the entire polyatomic ion. This is like the #1 place where I see people, this is like the #1 thing that people forget when we're doing ions. They forget to put the brackets and the charge. Like you'll get the perfect Lewis structure and then you forget the brackets and the charge, and then that's like a point. Okay, so let's do a Lewis structure for ClO minus. ClO minus. We need to figure out our skeletal structure. It's just 2 things, pretty easy. ClO. Then we need to add up our valence electrons. We've got chlorine, which has 7 electrons. We've got oxygen, which has 6 electrons. So we've got 13 electrons. What's wrong with that? We forgot the negative charge. How does the negative charge affect the number of electrons that we have? Are we adding or subtracting 1? we're adding one. Electrons are negatively charged. If we've got a negative charge, that means we've got one extra electron. So from the minus, we get one electron, and now we've got 14 valence electrons to place. To get this connected, we need one bond. So subtract out our 2 bonding electrons. That's going to leave us with 12 remaining electrons. We can place our 12 remaining electrons across oxygen and chlorine. They currently each have 2 electrons, which means that they've got room for 6, so we can count them in. Chlorine has 2. This is 3, 4, 5, 6, 7, 8. Oxygen's the same thing. It has 2 in the bond. This is 3, 4, 5, 6, 7, 8 for its octet. We've added in 12 dots, 12 electrons. Okay, so that is all of our electrons placed. Chlorine has 2, 4, 6, 8 electrons. Oxygen has 2, 4, 6, 8 electrons. Add in arrows so that our counting makes sense if you look at it later. So they both have their full octets. Why did I copy and paste this? So that I could get rid of all the numbers. Brackets and charge. If we don't put the brackets in the charge, it's not correct. So the last thing we do, brackets, and the charge was 1 minus, so we put a negative outside the brackets in the upper right corner. And that is a full and complete Lewis structure for the hypochlorite ion. Questions? Okay. There is more. So we can also have what's called resonance structures. So some molecules have more than one valid Lewis structure. For example, O3, which is ozone. Ozone, we're going to get these 2 options for our Lewis structure. The way that we get here, before we add in the double bond, we would have come up with, I'll show us here in the middle, oxygen in the middle, single bonds are oxygens on the end. We get to this Lewis structure. This is where we should arrive. This here in the center. This is where we'll be after step 3 of our process. And step 4, remember, is making double and triple bonds. So we get here, we look at our outside oxygens. Our left oxygen, our right oxygen, they're in the same situation. We've got 2, 4, 6, 8 electrons on each of them, 3 lone pairs, 1 bond. Same thing for the right oxygen. Our middle oxygen, though, has 2 bonds, which is 4 electrons, plus a lone pair, which is the last 6. Or gets it up to a count of 6. And that's not good enough, right? We want an octet, so we need 2 more electrons. And this is where the more than one Lewis structure comes in. Do we take a lone pair from the left and make it a double bond? Or do we take a lone pair from the right and make it a double bond? This is where the somewhat silly saying, if you come to a fork in the road, take it. It's a free fork. So are we taking from the left or from the right? The answer is yes, we're doing both. We're not going to make that decision. We're going to do both options. So one of these options, we double bond from the left. The other option, we double bond from the right. And so what we would do for this is we would draw both structures. Donk. Stop that. We draw both structures, and then we put a double-headed arrow between them to say both of these are valid. It's switching back and forth between them. In reality, it's a hybrid of these two situations. So these are an example of resonance structures. So that's a fun thing that can happen. This is a case where we've just got two resonance structures. It's possible to have more than two resonance structures. You could have 4, 5, 6, probably more, depending on how crazy you get with your Lewis structures. So resonance structures, in reality, the real thing is an average of the two. It's sort of like if you breed two cats, right? Two different types of cats, and you breed them together, you'll get something that's sort of in the middle. And that's what we get with our resonance hybrid. So it's a hybrid because we've mixed two things together, and in reality, it's about 1.5 strength bonds. That's what, if you can see here, zoom, that's what these, like, there's the whole line, and then there's the dashed line. The dashed line's like that. It's about half strength bond. In nature, electrons are often delocalized, like they can move back and forth over several atoms or bonds, which is results in lower potential energy. It's more stable, and we call that resonance stabilization. One of the big examples of this is benzene, which I'm just going to draw part of the structure for you. You don't need to know how to draw the structure of benzene. So benzene has these alternating double bonds, and it's a ring. These carbons also each have one hydrogen attached to them that I'm not drawing in. And this has resonance. In reality, it's the hybrid of these two. It's 1.5 strength bonds kind of the whole way around, and the electrons can basically just move around somewhat relatively freely. And this is a very, very stable molecule. Gives you cancer for interesting reasons. It's because it's flat. Okay, questions about resonance hybrids? We generally will not be drawing the hybrids, we'll just be drawing the resonance structures. Okay, some practice for you. Please write a Lewis structure for the NO2 minus nitrite ion. Don't forget to include resonance structures. Okay, we want a Lewis structure for the NO2 minus ion, including resonance structures. For symmetry purposes, nitrogen goes in the middle, and so we get O for our skeletal structure. And then we have to count up our valence electrons. We've got nitrogen that gives us 5. We've got 2 oxygens that give us a total of 12. We've got a negative charge that also gives us 1 electron, and so we get a total of 18 valence electrons. We have to place some down to get everything bonded together for electrons going into 2 bonds. and that leaves us with 14 remaining electrons. We can start adding those from the outside, working our way in. Each of these oxygens has room for 6. So we're going to do minus 6 electrons to oxygen the first, minus 6 electrons to oxygen the second. Just left and right respectively. We'd have 2 electrons left, and those will go to the nitrogen. If we do a quick check of our octets, our oxygens are happy. We prioritize them first, and so they're good. Our nitrogen in the middle, not so happy. It's got 2, 4, 6 electrons. It needs 2 more electrons, and this is where we invoke double bonds. We've got a choice to make. Do we bring it in from the left? Do we bring it in from the right? And we say yes. So the left option, the right option, and we say why choose when you can have both? Okay, so left option, right option. What else do we need? We do need brackets. Anything else? Double-headed arrow. Okay, so once we put the double-headed arrow in there, now we've got full and complete Lewis structure drawn. Questions? Looked like a lot of people got this, so that's great. All right. And then a little tester for us. Which of these structures is not a resonance structure? So one of these is not a resonance structure of this thiocyanate ion. What are we moving around with resonance structures? What moves? Bonds, electrons move in resonance structures. So we can move electrons around. For example, like we could move these electrons in and then give some electrons back to nitrogen, which would turn us into A. So A is a resonance structure. We could also go another step. We can take another one from sulfur, give another one back to nitrogen, and that would turn us into C. We cannot get B out of this because nitrogen is now in the middle and carbon's on the end. That would be a different ion because we've changed the arrangement. So B is not a resonance structure. The other two are resonance structures. All right, and we'll introduce formal charges. We'll go over them again next time. Introduce formal charges. So I'm going to start here next class, but I'm going to talk about it again today as well. So we've got some tools for figuring out what the correct Lewis structure is. In reality, there are more complicated Lewis structures. We've been looking at some relatively tame molecular compounds. And so we need a tool to come up with what's the best actual Lewis structure. And formal charge helps us figure out the actual best Lewis structure. So the formal charge of an atom in a Lewis structure is the charge it would have if bonding electrons were shared equally between the bonded atoms. So we're pretending that electronegativity is not a thing here and we're sharing all of our bonds equally. This is a fake charge that we assign to each atom. It's a numbers game. It's strictly a numbers game. We're just making stuff up, but it helps keep track of who's got how many electrons. Are they happy with the number of electrons they have? And is there a better arrangement? So we're going to ignore electronegativity, and it's a difference between the number of valence electrons of the atom that we're looking at and the number of electrons that it owns, quote unquote, in the Lewis structure. So a formula way that we can do this is the formula charge is the number of valence electrons minus the number of non-bonding electrons, basically lone pairs. We can also have a single lone electron, but generally lone pairs, plus 1/2 of the number of bonding electrons. Shared electrons. So a single bond gives 1 electron. I don't know why I started with the B of double bond, but a double bond turns to 2 electrons. The way that I think about it in my brain is, let's say that we've got this HCH, the oxygen up here. The way that I do it in my brain for calculating the number that it has possession of, so like for the carbon in the middle, if you just cut all those bonds in half, how many of the electrons are going to be on the carbon side? In this double bond, it's got 2. In the single bonds, it's got 1 each. So carbon has 4 electrons. It normally has 4 valence electrons. It's the same number that it has. So the formal charge is 0. And that's ideal. We generally want formal charges of 0. Oxygen, let's use the full formula thing here. Oxygen has 6 electrons. It's in group 6A. It has some non-bonding electrons. It has some bonding electrons. So we're going to do 6 electrons minus the number of non-bonding electrons. We've got 2, 4 non-bonding electrons. We also get 1/2 of the bonding electrons. So this double bond has how many electrons in it? 4 electrons. We're going to take half of that, which is 2. So what this turns into is 6 electrons minus 4 plus 2. So it also has a 0. So 2, 4, 6, because just the parts that are closest to the oxygen. Oxygen has 6. So you can use the formula. You can count them up, cutting the bonds in half. Whatever works for you. The goal is that it has the same number of electrons as it has valence electrons, just like by itself as an atom. And the rules, because of course there's rules, this is chemistry, got to make it more complicated. The rules is that the sum of all formal charges in a neutral molecule must be 0. The sum of all formal charges in an ion must equal the charge of the ion. So if we have a neutral molecule, we can have a +1 formal charge, or +1 formal charge. We can have a -1 formal charge as long as they cancel out overall to 0. Small formal charges are better than large ones. So 0 is the best. +1, -1 are fine. +2, -2 starting to get crazy. +3, -3 probably never going to happen. When formal charges cannot be avoided, negative formal charges should reside on the most electronegative atom. Nope, that doesn't work. I can't think of one off the top of my head. Nope, get out of there. I accidentally swiped to YouTube. And we're back. So if we've got a bond is between carbon and oxygen, and we have to give one of them a -1 or a +1. +1 or -1. The better option is to give oxygen the -1. It's more electronegative. I'm sure that we will see some examples of this in the examples next time. So if you're confused, we'll hopefully clear it up next class. Any questions at all about the Lewis structures that we covered today and some of the basics of formal charges? Cool, we'll stop there.